Last episode, you watched plain SGD limp along on one noisy example at a time. The gradient pointed roughly downhill. You took the step and it worked mostly. But roughly downhill hides a problem. Put that same optimizer in a long narrow valley, the kind every real loss surface is full of, and it stops walking and starts bouncing. Today you fix it with one idea you already know from physics. Give the ball some weight, momentum, same gradient, same learning rate, a third of the steps. Here's the valley. Our opti bowl L 0.5 W1 squared plus 5 W2 squared. Look at the shape, it's 10 times steeper across the W2 direction than along W1. That ratio has a name, the condition number, and here it's exactly 10. The minimum sits at the origin. You start at 350, 150, where the loss is 1738. The job is to get to the bottom. Sounds easy, it is not, and the reason is that steepest descent lies to you. The misconception: people think the gradient points at the minimum. It does not. The gradient points in the direction of steepest ascent. You negate it to go down, and steepest in a stretched valley means it points mostly across the valley walls, not down its length. At the start, the gradient is 350, 15 numbers. The W2 component is 15. The W1 component is 3.5. The arrow is screaming, go down the steep wall, barely whispering, go along the floor. Follow it literally and you climb the opposite wall. So watch plain SGD do exactly that. With a learning rate of 0.18, chosen right at the edge of stability for the steep direction, each step overshoots W2 and lands on the far wall, 150 to 120 to 0.96 to 0.768. It's oscillating, sign flipping every step while W1 barely creeps, 350 to 2.87 to 2.35. The optimizer is spending almost all its energy ping-ponging across a valley. It should be strolling down. That's the ravine bounce, and it's why a working optimizer can still take forever. Second misconception: just lower the learning rate, then it won't overshoot. Sure, drop it to 0.05 and the bouncing stops. But now look at W1, it contracts toward 0 painfully slowly, 350 to 3.325 to 3.159, shaving off a few percent each step. You traded a fast but wild optimizer for a stable but glacial one. The learning rate is one knob fighting two directions with opposite needs. You can't win this with a single number, and that's the trap momentum escapes. Here's the fix, and it's almost embarrassingly simple. Instead of stepping by the raw gradient, you keep a running velocity, an exponential memory of past gradients, v 0.9 by LRG, then T plus v. The 0.9 is the momentum coefficient beta. Think of a ball rolling, not a hiker redeciding direction at every footstep. The ball remembers where it was already going, and that memory does something clever for free. In the W2 direction, the gradient keeps flipping sign, plus minus plus, so successive contributions to velocity cancel. The bounce damps itself out. But in the W1 direction, the gradient keeps the same sign step after step, so those contributions accumulate, velocity builds, and the ball picks up speed straight down the valley floor. Same beta, opposite effect, exactly where you need each. Momentum doesn't average the noise away. It cancels what's inconsistent and compounds what's consistent. Watch them race from the same start. Plain SGD at LR 0.05 after 4 steps is still up at W1 hours, 2.85, lost 4.11, barely moved. Momentum at the same LR is already at W1 now, 2.39, lost 2.99 and accelerating. Its W2 wobble has collapsed to almost nothing, 0.075, 0.22 to 1, 0.17 to 1, while plain SGD's W2 is still limping down by halves. The gap widens every step. By the time both reach the basin, plain SGD has spent 78 steps and momentum 29. One honest caveat before the code: because beta has a failure mode too. Crank it too high, 0.99 and up. and the ball gets so heavy it overshoots the minimum and orbits it before settling like a marble circling a bowl. More momentum is not strictly better. 0.9 is the workhorse default because it accelerates the consistent direction without turning your optimizer into a pinball. Keep that in your pocket. We'll feel it again when we tune adaptive methods. Open07 momentum.py. It's one screen of honest code, the OptiBowl and its gradient up top, then two optimizer loops, plain SGD and momentum, sharing the exact same start, learning rate, and stopping rule. So the only variable is the velocity term. Each loop records its path and counts steps until the loss drops below 0.05. Then we print the two counts and hand the paths to the figure. First the surface, loss W is 0.5 W1 squared, 5 W2 squared, and grad W is W1 10 W2. Straight from the Bible, no autograd needed because we know the derivative by hand. Start is the frozen, 350, 150. Sanity check that loss start prints 17.38 and grad start is on 350, 15. If those two don't match, every path downstream is wrong, so we assert them. The plain SGD loop, pure steepest descent W, W, LR grad W, append to the path, stop when loss W, W, 0.05. We run it at LR Sobedo 0.18 for the figure's dramatic zigzag. The sign of W2 flips every iteration. You can see it in the recorded path. It crosses the threshold after 78 steps. Notice there is no memory here. Each step knows only this gradient. The momentum loop, one new line of state, V initialized to 0, and the update becomes two lines, VO beta, LR grad W, then W audio plus V. Same law you'd use for stability beta or 0.9. The velocity vector is what carries the accumulated W1 motion forward. It clears the same 0.05 threshold in 29 steps. Same surface, same start, same stopping rule. The only difference on screen is those two lines, the bookkeeping and the print. We store each path as a list of W1, W2 points for the figure, and we record the step count at the moment each crosses threshold. The headline line, momentum reached L 0.05 in 29 steps, plain SGD took 78, is just those two integers. Everything the figure draws comes out of these two path arrays, nothing is hand placed. So the lesson lands in one sentence. Momentum doesn't change where you're going, it changes how well you remember. And remembering cancels the bounce while compounding the descent. But notice we still used one learning rate for both directions. What if each parameter could earn its own learning rate, scaled by how rough its own history has been? That's the next idea, and it's the one that makes modern training actually converge. Next episode, RMSProp,